Hello, everybody. Thank you so much for coming today and sticking around with us for this last session. I'm Cooper Nederhood, and yeah, we'll be taking an inside look at Copilot code completions today. So for the first half, we'll be doing a little talk led by myself, and then in the second half, we'll be opening it up to a Q&A session with some other great folks on the Copilot team. So if you've got any of those burning questions about Copilot code completions, keep those in mind. That'll be a great opportunity for that. So GitHub Copilot was the first at-scale AI assistant for code completions in software engineering. So today, we'll take a look at how Copilot generates a suggestion. We'll look at how GitHub uses state-of-the-art machine learning techniques to increase completions quality and supercharge developer productivity. And then finally, we'll look at how code suggestions will continue to evolve into the future. If anyone is perhaps not familiar yet with Copilot code completions, here we show the traditional editor experience. In the top, in this example, they're the developers just writing a basic function to calculate the Fibonacci sequence. And then below that, we show what this looks like with Copilot enabled. So once the user stops typing, that sends a signal to Copilot that they're looking for a suggestion. So we show that suggestion to the developer in this dark gray text, which we call ghost text. If the developer likes what they see, they can accept that completion into their code base just by pressing tab. If they don't really like it and they want it to go away, they can do that by explicitly pressing escape, or they can just continue typing and it'll go away. In order to bring this suggestion to the developer, there's a complex series of steps happening behind the scenes. First, Copilot needs to build an understanding of what the developer is trying to do, what they're working on, so we can be sort of as helpful as possible. And we'll do this by assembling various pieces of code and various pieces of information that are available to us from within the editor. And we'll provide this as context to the language model. This will include things like the code in the active file immediately before the cursor, as well as any code after the cursor, which we'll include as a suffix. We know that sometimes in software engineering, the relevant code is not actually contained in the file that you're currently working on. So we'll also take code snippets from open tabs within the same programming language, and we call this neighboring tabs. We also know that sometimes metadata can be useful information to provide as context. So we'll include file paths as well as the current programming language as context. So we know also we're always trying to get this completion back to the developer as quickly as possible. So there is a finite amount of information we can provide as context to the language model. So given this finite token budget, we need to prioritize what we're going to include. So we'll prioritize that code in the currently active file. And then with any available token budget we still have, we'll break those neighboring tabs into code snippets, and we'll rank them based on how similar they are to what the developer is currently working on. And that way, again, we can just provide the most relevant context to the language model. So at this point, we've built a rich understanding of what the developer is doing, and we can actually get that completion from the language model. Again, we always want to be meeting the developer at this point of acceleration. So we want to minimize latency in any way that we can. One way we do this is by deploying these language models to data centers all around the world. And we'll dynamically route your request to whichever data center is like geolocated towards you, just to minimize any sort of communication overhead that request might incur. Anyone who's used these language models knows that they can be really chatty as well. They want to generate a lot of text, but that can sort of slow us down. And we also observe that about 85% of the time, our developers are actually just completing the current line that they're working on, right? So all of that extra code is just going to cause more latency and slow them down. So if the developer is in one of these instances where we see that they just want to complete the current line, we can preemptively tell the language model, stop generating code once you've completed that current line. And again, this just helps us get that completion back to the developer as quickly as possible. So at this point, we've gotten the completion from the language model. And we can do a little bit of post-processing, just making sure that things like the indentation are properly aligned with what's present in the current file. Sometimes we see that the editor itself will generate some maybe closing parentheses, so we can clean up any potentially overlapping code that would sort of be extraneous. We'll also run the completion through our REI filters just to make sure that it's safe. And finally, through code referencing, we can compare that suggestion to code in the public database and just see if there are any matches there. So this whole entire process, on average, it takes less than 300 milliseconds, and we're processing millions of completions all around the world every day. Since its inception, Copilot has been powered by state-of-the-art large language models from OpenAI. But as we saw in the keynote yesterday, we're increasingly partnering with some of these new providers to test new language models. And we're really excited to, now of course we'll test those first in Copilot Chat, but we're excited to see how those can improve the Copilot code completions experience as well. As you probably have seen, machine learning is a very rapidly developing field. And since its inception, GitHub has always integrated new models and new features that have come available and integrated those into the completions experience. Past improvements have included new base models with better overall code quality. We've also moved to optimized models to further decrease latency and just decrease our overall GPU load. We've also greatly increased the available context window. So back 2+ years ago, original first versions of Copilot only included a 2,000 token context window. That's now been increased up to 8,000 tokens, all without sacrificing those latency targets that we try so hard to push towards. We now natively support including code after the cursor by leveraging FIM mode. And we continue to update these models to bring that training date cutoff point closer to the present day. Now, these OpenAI models and large language models in general, which power Copilot, they've been trained on vast amounts of public code. So because of this, they're great generalist models, and they can provide high-quality code completions for a variety of programming languages in a variety of programming situations. But it's also possible to take that model and use it as a basis for you to go and train your own custom model on your data and your coding practices. So we call this process of taking a trained model, an already trained model, and then performing additional training, fine-tuning. So we find that a custom, fine-tuned model is most beneficial for enterprises that maybe use proprietary programming languages or very rare niche programming languages that aren't as represented as some of these popular programming languages in the public code. Maybe your enterprise implements private custom APIs and custom internal libraries. Or maybe your enterprise has company-specific best practices or coding styles. So by bringing your company's private, unique data to your custom model, you can allow your developers to have a more tailored experience. And Copilot just understands your code base in a more richer and deeper level. And so it can provide your developers with more tailored suggestions with how they use their functions, their APIs, etc. Crucially, all of the training, all of the model hosting and the inferencing with this custom model program is private and unique to your enterprise. So your data remains your data. Your data is never shared with it's never used to train any other models, and your custom model is never shared with anyone else. So this custom model program, it's currently in its public beta phase, and here we show a screenshot of what that training page would look like to the admin who can initiate that process. So if you want to go train a custom model, what this admin would do is they would select repos that from their organization that they want included in this custom model, as well as filter on what languages they want supported, if that's something they're interested in. So we're really excited to bring this to GA in the coming months and see how people are using it. So stay tuned for that. Overall, our mission is to push the state of the art in large language models for code completion. So while we're exploring leveraging techniques like fine-tuning to improve the code quality for our enterprise developers, we can also bring those same capabilities to bear to improve the code completions experience for all of our developers. So one way we're doing this right now is through researching what we call language-specific or code-specific fine-tuned models. With this program, we can take these generalist models and we can identify areas, especially in critically important programming languages. We can identify areas where these generalist models just aren't providing the completions quality that we'd like to see. And we can target those areas and perform additional fine-tuning to bring that completions quality back up to the level that we'd like to see. Again, this is a great opportunity for us to leverage our fine-tuning capabilities. It's a great opportunity for us to leverage the unique public open source data environment across GitHub. And it's a great opportunity for us to form partnerships with our Microsoft partners, who, especially those who have specific expertises in these specific critically important programming languages. For example, we recently partnered with the .NET C# team within Microsoft. Through our partnership with them, they identified that recent releases of .NET framework just weren't really as supported in Copilot code completions as some of these older versions of .NET that are more widely distributed through the public domain. So through this partnership, we fine-tuned a model on some of these C# and newer .NET framework libraries, and we're seeing that this new model improves in those programming areas. So this code-specific, language-specific work is it's in a research phase right now, but we're excited to see where this can go and where we can take this. So we also noticed that neighboring tabs, it's a great source of user intent and context. But we're also looking for additional ways to get relevant context and just to build an even deeper understanding of what the developer is doing. And especially as we increase the context window, this just gives us more flexibility and more creativity with how we can understand the developer's intent. So one way we're doing this is through what we call language-specific contextualization, essentially developing custom sort of language-specific prompt crafting and contextualization rules. For example, now in VS Code, if you're programming in C++, if you're importing a header file, whether that you have that header file open or whether it's closed, that header file will now be imported and can be used as context for your code completions. And again, this is something that we developed through a partnership with a C++ product team within Microsoft. So another great partnership there. We're, of course, also interested in building out a project-wide RAG approach in code completions. RAG has been something that has been great with Copilot Chat, and we're interested in building, taking those learnings into code completions as well. Some complexity that we always need to consider with this is that, again, code completions is so latency sensitive, and we always want to be accelerating our developers. So any sort of RAG approach has to be very sensitive to that, and it's a little bit more of a latency-sensitive environment than something like Copilot Chat that's a little bit lower touch. So we're exploring that right now as well. Copilot code completions, it's great at providing suggestions in the form of code insertions at your current cursor location. But as any developer knows, sometimes we're actually making a set of changes. And these changes might be at the current location, but they also might be all around the current file. And they might not be limited to just insertions. We might be deleting code. We might be modifying existing code. And we'd like to have Copilots help with these sorts of coding changes as well, not just these sort of insertions at the current cursor location. So we call this new feature Next Edit Suggestions, or NES. And with NES, you make a change, and then Copilot predicts the changes that follow. And it will present these to you as a sequence of edits, regardless of where they are in the current file. In the bottom example here, in the far left, in that left-hand side margin, you can see the black arrow, which is just indicating the location of this incoming proposed change. And then on the right-hand side of that, you can see Copilot is suggesting the insertion of this new function. So these changes can come at any point in your file, but they're also not just limited to insertions. We can also, with NES, it will suggest modifications and deletions. So because this is a much more complex change, we want the developer to still have an easy time understanding what this proposed incoming change is, so that that sort of mental load of reviewing it is as low as possible. So we can facilitate this review process by showing a rich diff view of what those incoming changes are. And you can see that in the top example here, where we're modifying this existing line, this existing Boolean condition. So this Next Edit Suggestions was originally developed by the GitHub Next team, and we're rapidly developing both the completion or the suggestions quality coming from these models, as well as further refining the user experience, just to make that as seamless as possible. So we're constantly exploring new ways to improve Copilot code completions and just provide users with even better completions. And with all these incoming changes, we need ways to estimate how these changes will affect production before introducing this change to users. We call this offline evaluation, and it's really hard to do offline evaluation with these AI assistants. Part of this is just because coding is such an open-ended task. There's so many different ways to write good code and, unfortunately, bad code. So offline evaluation is something we're always researching. Now, if a proposed change shows promising offline improvements, we can then run an A/B test to validate the effectiveness of this change. And through this, we can expose a small but statistically significant portion of real traffic to this change, as well as isolate a control group. So having these online evaluations just gives us a really clear insight into how these changes are affecting our users. So the combination of offline evaluations to gauge and prioritize the most impactful changes, combined with these online evaluations to really get a very rigorous sense of how these changes will impact the experience, give us a nice experimental agility and confidence that we're always making positive improvements to the Copilot experience.